Hi folks, welcome back to Physics with Captain Rod. The topic of this video will be angular momentum. This is meant to be just an introductory video to the concept of angular momentum. And before we talk about angular momentum, I want to chat a little bit about torque. So what we're looking at right here, this is like a top view of maybe a merry-go-round or something like that. So this object here is pinned, free to rotate about this axis here. And imagine that somebody is applying this force vector to this merry-go-round. Now remember that force vectors have what's called a line of action. In this picture, this would be the line of action for that force. And you notice that that line of action goes right through the pin. Also notice that this force would not make this object start rotating, right? So this object would not have what we would call an angular acceleration. And that's because this force does not produce any torque about this point. Any force whose line of action goes through your point of interest here creates no torque about that point. So now, how could I change that? Well, imagine that we take our force and we apply it maybe off axis, something like this. Oops. Now the line of action for the force here, if I draw it, and I'm going to go ahead and just draw a vertical green line here. So there's my line of action for that force. Now this force does create torque about this point. So remember from physics, if you've had this video, or I'm sorry, if you've had a physics class before, torque is force times distance. But the distance has to be perpendicular to the line of action. So in this particular problem, the distance we would use for the torque would be this distance. I'll go ahead and make this in red. Right there. This is the distance that's perpendicular to this force's line of action. If I move this force further to the right, this distance would increase and the torque would increase. Now let's talk direction. Torque is a vector quantity, as is angular momentum. The direction in this problem would be counterclockwise. Now, counterclockwise or clockwise is typically good enough in a 2D problem. If I were to actually attach a unit vector to it in terms of maybe this coordinate system here, if I've got I to the right, J up, K direction coming at you basically, this torque vector would be in the plus K direction. But generally speaking, clockwise or counterclockwise is usually good enough. If I move the force over to here, the torque created would be clockwise. Now, what I'd like everybody watching this video to pay attention to is that if I take a force and I multiply it by a distance perpendicular to the line of action of the force, I now have torque. And torque is basically the rotational equivalent of force. All right, so with that background in mind here, I'm going to get rid of this stuff and start chatting about angular momentum. So I'm going to get rid of, oops. Well, we'll just start out new here. All right, so now I'm going to put a coordinate system here so we can discuss directions as needed. Alright, so we've got an X, Y, Z coordinate system. And imagine I've got some sort of particle moving through space, and it's got a velocity vector that points, maybe this way. Now, if the velocity vector is in this direction, the momentum of this particle here also is in the same direction. So I'm going to go ahead and label this vector not as a velocity vector, but as a momentum vector, mv. If I pick a point in space here, which I'm going to call P, you'll notice that the line of action for this momentum vector, I'm going to draw this in green, up to about that point there. And you notice that there is a perpendicular distance from the line of action to P. I'm just eyeballing this here, so if it's not a perfect right angle, that distance is right here in the picture. The angular momentum of this particle about P is calculated by taking the linear momentum, mv, and just multiplying it by this distance here. I'm going to put r perpendicular. the distance that is perpendicular to the line of action for this momentum vector. So I'm just going to put RMV here, but take note that the R again has to be perpendicular to the momentum vector. And this quantity gives the angular momentum of this particle about this point. Angular momentum is a vector quantity. You'll notice that, in a sense, this thing, if you kind of think about it like a rotation, at the instant shown, it's kind of like this particle is rotating counterclockwise about this point. So in this example, the angular momentum of this object about this point would be counterclockwise, or we would say in the plus k direction. Now, again, angular momentum depends on this distance. Notice that, right, if I move, I'll just do the whole coordinate system. If I move this in such a way that the momentum vector goes right through the point P here, now the angular momentum would be 0. If I move it so our momentum vector is in this direction, now the angular momentum vector is mv times whatever this distance is, basically the perpendicular distance, except the angular momentum vector would now be clockwise. So this was just meant to be an introduction to angular momentum. It's equal to RMV, where the R needs to be perpendicular to the V. It is a vector quantity. Generally speaking, clockwise, counterclockwise is good enough. Not good enough for three-dimensional problems, but in two-dimensional problems, clockwise or counterclockwise is typically good enough. Should probably discuss units for a moment. So R is in meters, mass is in kilograms, velocity in meter per second. So your angular momentum has units of kilogram meter squared per second. So that's a little bit about angular momentum. I think what I'll do is just call that video a day and make another video about the angular momentum of rotating bodies. So hope this video helps introduce the concept of angular momentum. Have a great day.